Okay, so applications of inclusion and exclusion. This is the last section of chapter 7 in the text, and this continues on with section 7.5 that we just got done exploring. So these are a little bit more advanced applications, and so we'll go back and look at the general principle of inclusion and exclusion. And basically here we have finite sets A1 through AN. Then the number of elements that are in the union of those n sets is the number of elements in each one of the sets added together minus the intersection of two sets at a time, add in the intersection of three sets at a time, subtract out the intersection of four sets at a time, et cetera, et cetera. And there again, there is a fairly straightforward proof of this on page 504 of the sixth edition of the text. And in case you're wondering about the clip art, the guy in this picture is probably being excluded because he dresses a bit like a mugger, but can't really say that for certain. So in section 7.5, we saw that inclusion exclusion was certainly useful for solving different types of counting problems. And we'll see it applied in a broader context where we look at problems that exhibit none of a set of properties. For example, finding the number of primes, the hat check problem, and the number of solutions to equations with restrictions. So an alternative form of inclusion and exclusion is given on this slide, and this is useful for problems that ask for the number of elements in a set that have none of n properties P1 through Pn. So let A sub I be a subset containing the elements that have property P sub I. Number of elements with all the properties Pi1, Pi2 up to Pin will be denoted by n Pi1, Pi2, Pin. And that's the intersection of those sets. If the number of elements with none of the properties is denoted by n, P1 through Pn, and the number of elements in the set is denoted by n, then we have the number of elements in the set minus the intersection of those sets. And we saw that a little bit in the examples from 7.5. So how many solutions does x1 plus x2 plus x3 is equal to 11 have where x1, x2, and x3 are non-negative integers? X1 is less than or equal to 3, x2 is less than or equal to 4, and x3 is less than or equal to 6. So we let a solution have the property P1, x is greater than 3, P2, x is greater than 4, and P3, if x3 is greater than 6. The number of solutions is n minus np1 minus np2 minus np3, then add in the intersection of the two at a time, and then subtract the intersection of all three. And we kind of have to work this one out. The total number of solutions is 78. Number of solutions with x1 greater than 4 is 36. x2 greater than 5 is 28. x3 greater than 7 is 15. X1 greater than 4 and x2 greater than 5 is 6. X1 greater than 4 and x3 greater than 7, there's only one with that. And x2 greater than 5 and x3 greater than 7, there aren't any. And then the number of solutions with all three of them denied is 0. So we take 78 minus 36 minus 28 minus 15, add back in 6, add back in 1, and we get a total of 6. The Sieve of Aristophanes, you may remember this from elementary school, and if you don't, I'll probably have the worksheet when we actually teach the class, and we get to go through and do this. This is great for keeping elementary school students busy for, at least a little while. The one trick they probably didn't teach you in elementary school is you only have to go as far as the square root of the original number. So here we're looking at the first 100 integers, so we only have to go up to 10. But generally, we let the young kids run on a little bit so that, it gives them something to do, a little bit of break time for the teacher. And we certainly didn't know about square roots in fourth grade, so this was a real time waster for us, although, we had a lot of fun coloring in the sheet. So we can use the principle of inclusion-exclusion to count the number of primes, figure out how many of these that we should actually circle. In this example, we'll find the number of primes less than 100 for that worksheet. And if you recall, again, a prime number is only divisible by one itself. A composite is divisible by a prime not exceeding its square root. So we only need to work with the primes less than 10. Those are 2, 3, 5, and 7. So let P1 be a property that an integer is divisible by 2, P2 is divisible by 3, P3 is divisible by 5, and P4 is divisible by 7. Number of primes less than 100 is 4 for those 4 primes that we have, plus n, P1 not, P2 not, P3 not, P4 not. And we can do that calculation. Number divisible by 2 is 50. Number divisible by 3 is 33. Number divisible by 5 is 20. And number divisible by 7 is 14. Then we add in the ones that are divisible by 2 and 3, 2 and 5, 2 and 7, 3 and 5, 3 and 7, 5 and 7. Subtract out the ones that are divisible by 3 of those at a time, and then add in the one that is divisible by all of them. And it turns out that the answer here is 21. And if you did your C of Aristophanes correctly with your crayons and colored pencils and all our art supplies, you should have 21 of those circled. So another use for inclusion and exclusion is counting the number of onto functions. And here, how many onto functions are there from a set with 6 elements to a set with 3 elements? And B1, B2, and B3 are the elements in the range, and P1, P2, P3 are the properties that these elements are not in the range of that particular function. And recall, the function here is going to be onto if and only if it has none of the properties P1, P2, P3. And the formula we get for this is 3 to the 6th, because that's the number of possible functions, minus 3 choose 1, 2 to the 6th, plus 3 choose 2, 1 to the 6th, minus 0, and that gives us a total of 540. And it turns out that these correspond to a particular type of numbers called the Stirling numbers of the second kind. And you can see that these numbers are going to, grow pretty rapidly. But we can use them for certain types of problems. For example, number of ways to assign 5 different jobs to 4 different employees. If every employee is assigned at least one job, they could be assigned more than one job. And that's a direct application of Theorem 1, the Stirling numbers. And here we have 4 to the 5th minus 4 choose 1 times 3 to the 5th plus 4 choose 2, 2 to the 5th minus 4 choose 3, 1 to the 5th. That's 240. You can see these numbers are going to grow if you get, beyond, 5, or, you get up to 20 or 30. And that's why, job assignments is a particularly difficult problem to solve. Another application is the hat check problem, and I'll tell you the story about the dogs in class. The clean version is a new employee checks the hats of then people at a restaurant. When the customers return for their hats, the checker gives them back hats at random. What's the probability that no one gets their correct hat back? Well, turns out there's a related problem, and the related problem is a French game of cards called Rencontres. You have 52 cards in a deck. They're laid out in a row. The cards in the second deck are laid out on top of the first deck. Your score is the number of matches that you have. What is the probability that you get a score of 0? And we'll get in a group and we'll play a few different games with a smaller size deck. And I'll ask you how many games you had with no matches. And, we'll do this empirically. We'll, write this out on the board and get a calculation. Well, after playing this game, well, you're probably thinking, hey, that game's kind of deranged. And you're right. In fact, a derangement is a permutation of objects that leaves no object in its original position. So this will be, again, you getting a 0 score in Rencontres, or no one getting their hat back at the hat check. And so as an example, if you have numbers 1, 2, 3, 3, 1, 2 is a derangement because no number is in its original place. And it turns out the number of derangements is given by this formula in the fourth bullet point. And as n grows large, as you take the limit as n goes to infinity, it interestingly converges to e to the minus 1, or about 36.8% chance. And so that's the solution to the hat check problem. And to recall and trace, you should have about 1/3 of these, or a little more than 1/3 of these, coming back with scores of 0. So that's a wrap for the chapter. We discussed recurrence relations and their uses, such as Fibonacci numbers and towers of Hanoi. We got to see how to solve linear homogeneous recurrence relations in 6 steps or less, probably much to our chagrin. We looked at applications such as divide and conquer algorithms and their associated recurrence relations that led us to the master theorem. Some of those divide and conquer things like binary search and merge sort are definitely useful. And then we learned about inclusion and exclusion and saw applications of that to solving counting problems. And last but not least, we also looked at generating functions. So next up is relations, and hooray, you made it through the worst part of this chapter. Thanks so much for watching.